watch it again. Okay, so now I will describe how we can run a quantum algorithm on a quantum computer provided in the cloud by the IBM. So, and as an example, I will, run the Dice-Jozsa circuit that we just saw, and we simulated it on a quantum simulator. We will now run it on a quantum computer. So for that, let me share my screen again. Okay, so this is the circuit that we had just drawn, this Dice-Jozsa circuit, and we just saw okay, we can run it using the simulator, and we saw perfect result that when 00 came out, it meant that it's a constant circuit, and when I used a balanced oracle, for example, F01 half x, and if we run it again, we okay, so it's only F01 half and there's no x. Let me remove this x. And we saw that there is something other than 101 that is coming in the results. So it means that this is a balanced oracle. But let's now run it on IBM computer. And for that, I would like you to make your account on this quantumcomputing.ibm.com. And once you go there, and after you have made the account and you log in, this is a screen that you're going to see. Okay. So on the right side is the list of notifications for you and some general information. And over here, you see your home screen. And IBM, provides this facility that you can compose a circuit right online in their system. Like you can launch a composer from here, and instead of writing your code separately in a Jupyter notebook, you can write it over here. So since I don't, usually use it, you see when I have come here, it's giving me a welcome message. But you can use these circuits and make a graphical program. Okay. For example, this CX circuit, I can put it here. I can, have this T circuit. Let's say if you want on this 1th qubit, you can put some other, identity and some. So you can compose your circuit right here if you like. Okay. And then you can run your circuit right from here. But that's not how usually we do it. And you can see that your code is also appearing on the right side. What we do, we usually, write code in Jupyter and then call the quantum computer right into the Jupyter notebook, but you can do it right here as well. All right. So let me go back. And you can also, work in this lab, which is which also has your previous files, etc. For example, I have done some work in this part, so I have my previous notebooks over here. So this is almost like a Jupyter notebook. You write your program here, and you run it just like a Jupyter notebook. So this lab is essentially an online Jupyter environment for you. So that you can use. So this is another way of running a program on a quantum computer, if you like. But let's go back again. And let me see. So composer, and so this is where we can go to services, and this is where the dashboard is. Okay, so I'm back at the dashboard, and you can see a summary over here. So right now I have 0 programs that are being running, and there are 9 systems that IBM has allowed me to use because I have a free account. That is the usual account that people have. And I have also actually applied for an educator account that might give me preferential access to run some programs, but that's under process right now. Anyway, when you will make an account, this would be this free account that I have right now. And they have allowed me to use, 9 actual quantum computers and 5 quantum simulators. And if you, want to see their list, it should be appearing. Let me see at some point. And systems. Okay, so this is the list of all the systems that are available out there. And you see, for example, this IBM Q Montreal, this is a 27 qubit computer, and its quantum volume is 128. I will have a full lecture on quantum volume, how you can characterize a quantum computer. I mean, what number gives out the quality of a quantum computer. And actually, it's not the qubit, it's the quantum volume. But right now, you can keep this thing in mind that bigger the quantum volume, the better and more powerful quantum computer is. So that's actually the measure. For example, if you see this IBM Q Manhattan, this has 65 qubit, but its quantum volume is only 32, which means that this Montreal is actually a much better computer than Manhattan computer. Similarly, this is worse than this one. But if you compare Dublin and Manhattan, so Dublin is also better. Similarly, Brooklyn have only 32 quantum volume, but it has 65 qubits. So number of qubit means that how many qubits you have that you can do operations on, and this includes total number of qubits. This is include working qubits and cilia or any other auxiliary qubit that you have in your computer. And you can see as you go down. So the maximum quantum computer that they have made available is the 65 qubit, which by the way is not available to free account holder people like us. There are some organization and some universities that have partnership with IBM, and those organizations have access to these more powerful quantum computers. And the IBM also, have another collaboration project. So where individual people can also collaborate with the IBM researchers. If they, somebody has a very good idea that requires more qubits to run than is freely available, then you can work with them and they can run the program for you if they think that it's worthwhile. But anyway, so you see that there are these smaller computers down here. For example, these 5 qubit, 7 qubit, even there's a 1 qubit quantum computer as well. But most other are 5 qubit quantum computers and 15. So you can check from here that what is their status. For example, if I click on this IBM Q5 Yorktown, and I see there are 311 jobs that are pending right now on it. So if I submit my job to this, quantum computer, it's going to wait a lot because 311 other jobs are there. Once they're executed, then my time will come. And then you can see from here, what's the, average CNOT error, what is average readout error, and these coherence times. So smaller error and longer coherence time are better. And similarly, you can measure, you can visualize the qubit map. For example, this qubit 2 can be, can have entangling operation with this 0, 3 and 1, 4. But for example, this 4 qubit can only have entangling operation with 3 and 2. It can't have an entangling operation with 0 and 1. And if your program requires entangling between them, it will have to be teleported to the other qubit and so on. So you can, get an idea about a quantum computer by clicking on it. Okay, so so this is actually one of the worst computer, this Yorktown, because it has a quantum volume of only 8. Except this Armonk, which has only 1 qubit. These 8 quantum volume computers are the worst because they have the highest number of errors. Even though, for example, this 15 qubit quantum computer have 15 qubit, but its quantum volume is 8, which is even less than this 5 qubit Manila quantum computer with the 32 quantum volume. Okay, so any question on these quantum computers? let me see where is that list which tells me that what computers I can use. By the way, these are simulators that are available. So this COSP simulator is the general simulator, and this is a 32 qubit simulator. So you can simulate 32 qubit in any general circuit using this COSP simulator. Similarly, the state vector simulator is also 32 qubit. These, higher qubit simulator, they are special purpose simulator and they are not general purpose simulator. At least that's what I know from them. Okay, so let me find the list of, programs that are list of computers that I am allowed. Okay, so these are the jobs that I have submitted and executed, by the way. For example, this one, if I click it, because sometime when I submit some job from here, it's taking a long time and I have to go somewhere, so I go, but the job is not lost because its result are already, they are available over here. Okay, so unfortunately, let me see. Okay, because I wanted to click on the tabs, but then was being clicked on the Zoom functions. So this is the job that I submitted, and these are the results that are already available here. So even when I submitted the job and I went away, my job still was executed, and the results are available here that I can see later on. So, okay, let's now see how you can run a job on one of the quantum computer. So the method is this, that you see this API token. So you have to copy this token. If you click on this button, you will regenerate. But if you just click on this, so my token is copied. And once my token is copied, I can come back to my Jupyter notebook, and you see from here I'm in Qiskit. There is a package IBM Q that helps connect with the quantum computer. So in this IBM Q, so I call this save account command. So in the save account, from in this single code, I copy this token and then I write override true, because there might be other tokens after you start importing them. So this will overwrite it. So you can just see what I copied from here. From there, it's like this. So this is exactly the same token that I also, this is ending at 28. So this is 28. So this is a token that I have copied from there that is already in my account. So when I run this box number 20, now my Jupyter notebook knows through this token that after this, when I call a quantum computer, this program has to be run on IBM quantum computer, and it will access my account with this token. And this is the key point of linking your account with the IBM quantum computer that are available in the cloud. And it's real super easy. All you have to do is copy your token from here and paste it here. Now, once my account is saved and I want to use it, I can now use this provider as IBM Q.load account. So with this, I will load my account, and then I can now select my backend using this provider.get backend, and here I will specify my quantum computer. You can see when I was running this program, my backend was coming from this basic air, okay, which is accessing this quantum simulator, and this is what my backend was. But now I'm specifying backend as a quantum computer. But now I want to specify a quantum computer which is not very busy, so that I can quickly run the program to show you, but if I don't have access to, and I don't have access to a quantum computer, which is, available right now, then we'll just submit and then I'll show you the result that I already have. So let's see this Lima, because this is a very crappy quantum computer anyway. So there are only 42 jobs. So people know that don't try to submit a job to this one, because it's a crappy quantum computer with only a quantum volume of 8. But for our purpose, this can just illustration
It's
purpose.
maybe where you do not have access to the system.
It's actually over here, it's written on everything. So that's why I was trying to find a
आप
list.
थोड़ा सा scroll up करें, यहाँ पे लिखा हुआ है ना all, ऊपर जाएं जरा, यहाँ पे लिखा हुआ है all systems, यहाँ पे down arrow दबाएं, your systems पे.
Yeah, I know that it always shows, okay, you don't have access to this, but it works on 9 of these. And those usually 9 are in the bottom of the list. Okay.
सर एथेंस पे तो पहले काम हो जाता था, मेलबर्न पे भी हो जाता, यॉर्कटाउन पे भी हो जाता था.
Yes, it works. So I'm not doing it on Yorktown right now, because it has 285 jobs in the queue already. Last night when I was working, it only had 1, and I was able to run quickly, on this thing. So usually I think the best time to work on these quantum computers from Pakistan is in the evening here, because when it is evening here, it's almost morning in the US, and most jobs are coming from US and Europe. So people who work during the day and submitted their jobs have been executed overnight. So when it's evening in Pakistan, it's a really nice time. You will see most of the computers on a lighter load. So in the evening here, when you do this processing, this can happen quickly. Let me see this Quito, how many jobs this has. So it has 8. Okay, let's use this Quito if it is available to me. So this is IBM Q2. So let's specify this Q2. It will tell me right here if I'm allowed to use it or not. Perfect. So I can use it. Let me run it. And we can, wait a little bit. And let me show you the output from an actual quantum computer. So you see, this was the output that I got last night. And actually, I was supposed to get 101, but this quantum computer, I used Yorktown last night. It's so much noisy that it gave me 111 with the highest probability. But anyway, let's see how good, this Q2 is. And in the meantime, if you have any question, please do let me know. By the way, you can come here and see the status of your job. Let me refresh this page. So you see, I now have 1 pending job. I'm clicking on it. And should show me, let's see this view all. And this one, yeah, this is pending right now. But if I click on it, this can show me the details of this job. So it was created, transpiling, it was validated, it has been validated. So validation is good. And it is expected to run in 6 minutes. This is good news. So in 6 minutes, I'll have my result. So the result would come, right in this notebook already. These are some of the commands that you can use to monitor the job, but let's not worry about these right now. So I'll plot this count. So as soon as this job is run, the results would be in counts, and I will plot this counts on this histogram. And you see, our result is expected like this, because I should get 101 with probability of 1 if my quantum computer is completely without any noise. But since this quantum computer does have a lot of noise, so we should be expecting other outputs as well. But hopefully this 101 will have the highest probability. So let me refresh it to see how much time is left. So it's going to run in 2 minutes. That's good. So does anyone of you have any questions? Okay, it seems like it has run. I have still not been able to find that list of computers that were available to me. I don't know if they have changed this view.
Say on the run on circuits algorithm, there's a view all. It's showing you
The
9 systems.
Sorry, please go ahead again. There was somebody at the door.
So on the page before, it was showing that you have 9 computers and it was giving you a view all option. If you go to the page before you were here.
Yeah, so it's showing me that I have 9 computers and
Yes,
5 systems. Okay.
So you should select the view all button.
So this one?
Yes, sir.
But this actually doesn't just show what I can run. This shows everything. It shows all 32, systems. You see, these are programs, these are systems. So all 32 systems are being shown. Oh, this is a better view actually. That if you make it a table, it shows, pending jobs right here. But this unfortunately still doesn't show which we are allowed to use.
Excuse me, sir.
Mm-hmm.
सर कंप्यूटर के नाम के साथ जो सिटी लिखा हुआ है तो ये उधर स्टेशन है ये कंप्यूटर लाइक यहाँ पर कोलकाता
No, they're just giving them names in the names of different cities of the world. I don't know the rationale of giving different particular cities name, but they might have some reason, or maybe they're using just famous cities of the world to name them.
ठीक है सर.
Okay, so we are lucky that the computer Qto that we selected to run our job, first of all, was not very busy, so we got results very quickly. Most of the time, on the average, you might have to wait overnight actually to get your results back. But anyway, and our second, luck comes from this fact that we were supposed to get 101 with probability of 1, which we didn't, but we still got it, in a way which is pretty convincingly telling us that the oracle that we implemented was a balanced oracle, because 000 has a probability of 0.021 and this 101 has a probability of 0.79. But this is how generally you will see the results from a quantum computer. And see, the quantum computers are noisy and they have a lot of errors, and the errors and noise is coming from 2 parts basically. One is from all of the program that you have, like starting from initializing qubits to running different operations and processing your information. And then there's a last part, which is the measurement part, and then doing measurement. So error noise can come from measurements as well. And later on we will have a couple of lectures where we first of all see how to characterize quantum computer by measuring their quantum volumes, and also we will be able to have a way of reducing or mitigating measurement errors as well. We will essentially measure characterize a quantum computer by measuring its qubits in different states, and then knowing beforehand that okay, what type of errors it puts during measurement, and then we will, reverse engineer these measurements and reduce those measurement errors. But anyway, that will come in the next week. For now, if you have any question, please let me know. Otherwise, we will move on to Bernstein-Vazirani algorithm.
सर मिड के अंदर या फाइनल के अंदर तो हमें क्वांटम कंप्यूटर नहीं यूज करना होगा ना, लाइक वी कैन
Most likely not. Okay, because but I will give it to use, in homeworks, because you will have few days.
क्योंकि वो भी आपने कहा that we might have to wait overnight.
Yeah, so you're absolutely right. In the timed exam, if it is a a couple of hours long exam, then it will usually not be possible to run on a quantum computer, because you may not have access to a computer that is free right now.
सर क्या आप वो लाइन दिखा देंगे सेव अकाउंट की?
Okay, let me show again. So this one.
सर तो जहाँ पे कोड इनपुट होता है आपका जो टोकन है।
Oh, on the IBM website over here.
जी नहीं, हाँ बस ये लाइन मुझे राइट टू राइट तक दिखा देंगे।
Yes, so what you have to do, this is actually your dashboard. So they used to keep it at some other location, but now they have put it just on the dashboard. So you just click on this, copy button, and your token will be copied.
Okay, sir, sorry.
Okay, and it would be automatically generated. When you make an account, your token would be there. If you want to change the token, because maybe somebody has access to your token and using your account, you can simply click on this button, and now your token is going to be regenerated. I'm not going to regenerate because I have many files where this token is written. But after this course, when you will have access to these files, I might change the token so that none of you are using my token. But I can change this token by clicking, and then I'll have to copy the token again to my file. Okay.
Okay, sir.
Perfect. And any other question?